Well, thank you everyone for coming on. This is our next in the round of the PERG EWI series coffee breaks. And today we are talking to Patrick at ETC, um, and he will be giving us an introduction to data types and technologies to kind of talk about the history of lighting control. Give thanks to our annual sponsors who make this all possible. Anton Bauer, Ari, Astera, Do Close Lenses, Lightgear, Panavision, and Taylor and Taylor. So thank you to them for supporting us as always. And as I said, we're going to hear from Patrick Stewart, who is an outreach and training specialist at ETC, one of the largest and foremost lighting control companies in the country. So thank you, Patrick, for being here. And we can turn it over to you.
So let's kind of start off with something kind of fun here, and let's talk about a quote. So communication is a means of sending and receiving information such as phone lines or computers. So data types and topologies is communication. It's how our devices communicate with other devices through some sort of a cable or a media of some sort. So that's the essence of what data types and topologies is all about. So a little bit about me. I started with ETC in 1999 as a repair technician. Before that, I did 10, 11, 12 years, something like that on the road. I've evolved through ETC as a field service engineer, documentation and training, a couple other things. And now I'm the one of the outreach and training specialists. I also have 26 years now in the Navy as a Navy aviation electrician's mate. So that is troubleshooting aircraft, the electrical systems on aircraft. So troubleshooting and data and communication are all kind of things that come pretty natural to me. So I will try not to talk over anybody's heads. If at any point in time you got a question or I lose you, I'll ask that you just kind of raise your hand. And then I'm hoping that Allison or someone can kind of clue me in that there's somebody needing a question answered because I only see 3 of you. So who helped with this, putting this presentation together? Well, Steve Terry is a longtime member of the ETC family. He is also more than just a dude in the room. When they created DMX 512, he was one of the primary folks in the room when DMX was created. So a lot of this comes from the very beginning. So how we got here, Steve was part of that. So let's kind of jump into this and let's talk about what we're going to cover. So we're going to talk about the evolution of the control that we use today, how it became what it is. So that's manual control. Then we're going to go into some other forms of what we can kind of call remote control, networking, and then we're going to talk about what's kind of coming down the pike. So what the future can hold and what is somewhat present in some fixtures as we speak. So in the beginning, we had these things called rheostats. Big, if anybody didn't use them, it's a lever connected to a big transformer on a wheel. And as you change the resistance by moving the lever up and down, the light would get brighter or dimmer. It was a pretty rudimentary process, but it took lots of arms and legs to make it work. And they took up a lot of space on the sides of stages. So couple of things that we wanted to think about. One is that now we have people around high voltage dimming lights up and down. So there was a desire to separate humans from high voltage. And there was a desire to not have this stuff on the side of the stage any longer. So they were looking for a way to what we can kind of refer to as remote the high voltage work from the actual person pressing the buttons. So that evolution went to analog control. And this was a DC control, so low voltage DC control that this is a picture you're looking at on the left-hand side here of the back of a lighting console. So you would have a wire for each dimmer or each circuit, and then a common that would go down a cable. And you can kind of gather in today's world what that would involve. It's a massive cable to do all that, but it got the dimmer away from the console, so the dimmers could move into closets in the basement or way off stage, and then the lighting control that the person would actually be working on could go into what we now refer to on stage as a booth. For sets, it can be off to the side somewhere, and your dimmer could be in a completely other side. It can be in a whole nother room in the studio. Lots of different options once this kind of concept came to be. Then we went into early digital. I like to consider this the Wild Wild West. I was in the middle of it. So each manufacturer had their own way to communicate with their equipment. And they didn't share the information. They all did it differently. And, rental houses, which most of you are part of, were stuck in situations where we would either have to buy gear that was all identical, so same manufacturer, or we had to have and rely on third-party manufacturers to make converter boxes. So Doug Fleener was one of those companies that made converter boxes at the time, still in business, making all kinds of cool little DMX toys. And then in some cases, you'd have multiple boxes in between the console and the dimmer to make them communicate with each other. So do I have any questions so far? Okay, so let's get into kind of how things kind of started to narrow down. There were two primary companies leading the industry at the time. One of them was Strand. Strand had a protocol called the CD80 protocol, or the AMX 192. It could control up to 192 dimmers on a single cable. It used a 4-pin XLR, which probably looks very similar to what we use today. It wasn't very stable, which is one of the reasons why it wasn't the kind of the leading technology that we settled on. The other big manufacturer at the time was Colortran. So Colortran had another protocol that was also 192 dimmers, and it used this RS422, which was a balanced communication, so it was a lot more stable, which means basically, and I'll show you a picture here in a little bit, where whatever noise or interference showed up on one side of the signal, it would equally show up on the other side of the signal, and they would counter each other out. So it was a lot more robust. If you notice this connector on the right-hand side of your screen, it looks identical because it is the exact same 5-pin XLR cable that we use today. This was the leading kind of protocol that the group decided to go with. And then that brings us to RS422. I do not expect you to remember this unless you are a nerdy type person like me that likes things like this. This is the protocol that DMX was written on. Its original protocol only allowed for 16 receiving devices. 32 is what DMX 512 was expanded to. There's some caveats to that. If anybody is running into what we call eighth load devices, which means 8 of those eighth load devices equal one device. So in a sense, you can have 256 of those devices on a line. I don't want to lose anybody, but if you are running into those and you want to do a sidebar conversation after we're done, I'll be happy to talk in more specifics with that. One of the problems that they were having back in the late 80s, early 90s, when this was coming out, is manufacturers were using 3-pin connectors. Those of us that are fairly versed in production know that 3-pin is sound cable. Sound cable is not even close to the impedance or the electrical characteristics required for DMX. So they were using sound cables to run DMX, and the manufacturers were also using 3-pin XLRs. So it kind of opened itself up to very unstable, very unpredictable. And it took a while for DMX to kind of become stable, where people were confident in its ability to do things, because analog was rock solid. You can't really mess up an analog control system. Part of what helped this along was the manufacturers that would stop using the 3-pin and started using the 5-pin XLR. That helped things quite dramatically. And this is why it matters. So part of the protocol requires that the cable be a 22 gauge and a certain number of twists per foot, and then a nominal impedance of 120 ohms. Now, where this comes into, where it becomes very important is when this signal goes out down the line, when it gets to the end, it tries to turn around and come back. And if it turns around and comes back, now you got signal flowing in both directions, and they can confuse the receiving devices. So we do what's called a termination at the end. So we need to know what the nominal impedance of the cable is so that the terminator at the end matches it and acts as a sponge. So when that signal gets to the end of the line, now the sponge or the terminator sucks it up and it doesn't let it reflect back down the cable. Those of you that are using RDM in things, the receivers nowadays, so like a lighting fixture or anything that's receiving DMX from the sending device, are pretty robust in that they don't necessarily need to be terminated anymore. But the RDM is a two-way communication. So RDM will get very cranky if it's unterminated. And you can lose that capability to get that bidirectional communication with your receiving devices. All right. So physical specifications. So these are very important. And back in, the 90s, this is some of the stuff that wasn't really understood, and it was not being taken into consideration. So daisy chain topology is the first one. This is very hard not to accomplish today with the way equipment is manufactured, with an in and an out, and the cables that we can purchase all kind of almost force it to be a daisy chain. And I'll show you, I have a diagram towards the end of this presentation that will kind of show you what that physically looks like. But that's where you're plugging into the first device, and then you just out to in, out to in, out to in down the line. So a stub or a T or a Y cable is anything that breaks that. So it's where you got one input and two outputs. As long they're technically cool if they're under 12 inches, but it adds a lot of noise and reflection to the signal, which will degrade over distance. And there's the end-of-line termination that I talked about. So that's where that 120 ohm resistor, and if you want to make your own, it is between pins 2 and 3 on the connector. Some more physical, I'm having a hard time saying specifications today. So 1986 is when this when DMX was developed. That was also easy for me to remember, the year I graduated from high school. It is now called ANSI E1.11. It has been updated and to include RDM now, because RDM was not a thing back in 1986. But the basis of the specifications of DMX 512 has not changed since it was introduced in basically 1990 is when it was really kind of introduced. It says that you have to have one transmitter, only one transmitter, and 32 receiving devices. This is again where that a lot of our smaller LED lighting fixtures that are just like a single, not a multi-parameter fixture, are not a full load anymore. So that's where you could get your eighth load devices, and now you can, as long as the load doesn't exceed 32, you're good. The maximum cable length of 1,640 feet or 500 meters is also very important. This was, not only was this being, I guess violated is probably not the right word, but we were not paying attention to the distance, but when we were using the non-spec cable as well, this is also part of what was causing all the unreliability issues back in the early days. So how does it work? Not going to go into super detail, but it's a packet of information. There's 500, what I like to refer to as mailboxes. So if you think of your DMX cable as a street, you have 512 addresses on that street, or 512 mailboxes on that street. Today, some of those mailboxes are a single family house. So you have one mailbox at one house. And in some cases with a multi-parameter fixture, you have an apartment complex that has multiple mailboxes inside of it. So it will talk to all 512 mailboxes 44 times a second. So it's pretty fast. Back in the dimmer days, it was way more than we ever thought we would ever need. But in the multi-parameter fixture world, where in an LED or a like a rotating gobo module or something that kind of has a really fast reaction time, it can see lost packets. So it can be told in one packet to do something and then not in the other. And depending on how that light is set up to work, it might flicker at you because it's trying to do all the changes, or it might not do anything. It might just sit there. So that is where we want to make sure that the integrity of our signal stays intact, because these new multi-parameter fixtures will try to do what the signal is telling them to do, even when it's just noise. It's not actually being told to do something. Another kind of fun little tidbit here is when you look at DMX from like a viewer, an ACN viewer, you will see that it doesn't say full. It's 0 to 255. So there's 255 steps. That is why you will find two pan and tilt channels for an automated fixture, because as fixtures are panning over 360 degrees now, you only have 255 steps. That means it's moving over a degree each time you try to go up a level. So the way those fine and coarse channels work is you'll go 1 through 255, and then you'll move a course one pump. And then so now you have 255 steps between each step of the course. So whatever 255 times 255 is, I can't do the math. So the transmitter, like I said, sends the packet, and then each of the addresses is told what to do, and then it repeats itself, and it does that 44 times a second. Another fun little tidbit I like to throw in here is if you're using any like small LED drivers, like for tape and stuff, they're telling you to set up dip switches. So if you look in the middle line, so the top of the smaller font, you'll see that each of those dip switch settings has a number value. So it's 1, 2, 4, 4 and 4 is 8, 8 and 8 is 16, 16, 16, 32, right? So you go down the line. So if you just add up, this I think was supposed to be 177. I can't see my notes because I don't have two monitors. So if you add up 1 plus 2 plus 4 plus 16 plus 64, you get that number. And that's the science behind how that math works in your dip switch settings. Yes, there's apps that will tell you how to do it, but in the event you get stuck and don't have your phone, if you can remember this 1, 2, 4, 8, 16, 32, 64 numbering scheme, you can actually get there just in your head, or at least with a piece of paper. Any questions so far? Still doing good?
Why 44 bits a second?
It's just that's what they determined. That back, so you got to think back in 1986, that was super fast. Like they would never need anything because a dimmer was so coarse at that time. Even trying to future proof 44 times a second seemed outrageous. Now we'd probably like it to be higher. But yeah, that's just what they had to work with back at the time. It's a great question. Right. So why does our system topology matter? So if the electrical characteristics of the signal are modified in any way, the receiving device could potentially not recognize it and then not respond. Or it could recognize it too late and then responds erratically, and then things start to go a little haywire. So I have some pictures of what that signal looks like. Oh, after I show you this one. So back to data pin number 1 on the XLR is your common, and then you have a plus signal and a minus signal, which I'll show you a picture of. The proper termination I said already is 120 ohms. I'm saying it multiple times because I want you guys to hopefully remember it. Pins 4 and 5 are not used. A neat little tidbit is at one point they were considering doing RDM on pins 4 and 5, but many installations in don't even have anything landed on pins 4 and 5. So it would be, they had to figure out a way to do RDM on the backbone of existing 3-pin. So here's what that view looks like. So this is that plus and minus. So you have the plus 5 volts and the minus 5 volts, and you can see them equally opposing each other. And that is, again, so that any interference that appears on the cable is equal on both and then just is counteracted. So it doesn't really happen. So the amplitude, so that spike, that upward part or that lower part needs to be of sufficient amplitude. And it should be the same for both plus and minus. You want so this is a scope shot. Don't try to analyze what it actually means other than just to look at the signal, the electrical characteristics of the signal. They're nice and sharp corners. It's up, straight down, right? All that stuff matters when you're talking about the number of times it's sending ones and zeros in a given second. So this one is going to be unterminated. What we were really hoping to get when we did this is to see the second waveform coming back the other direction, but we could never get it to work. But what we could consistently see over and over were these overshoots, and you see them on the I don't know, do you guys see my mouse? So you see them here on the leading edge, and you also see them on the trailing edge. Any of this stuff could cause it to the receiving device to not recognize the signal. But what we are more concerned about is the coming back the other way. And we were able to see reflection is what we call it. We were able to see a reflection in a later shot, which was, we could never figure out why it worked, but you'll see it here in a little bit. So over termination can be a thing. So like opto splitters and some lighting fixtures have terminations, terminator switches on the outsides. Dimmer racks have terminator switches on the outside. And if you turn too many of them on that street, you will bring the amplitude of this signal down. So this is the exact same signal you saw in the first shot. We now added devices and terminated them to decrease the amplitude. So if I bring this amplitude down far enough, the receiving devices won't recognize it. They don't see it as a sufficient high enough amplitude, and they don't even recognize the ones. Opto splitters is probably the one I see and hear about the most nowadays, because each opto splitter has its own self-terminator. There's a lot of lighting fixtures out there that do self-terminations. So it's possible, and it's a mechanical connection. So if the cable is inserted on the output side, it pushes the terminator back. So it's possible that terminator can be left back, as in it mechanically doesn't pop back to unterminate. And you can over terminate inadvertently that way. And this is our fun excessive capacitance. So this is our mic cable. So you can see, especially down here, you can see how rounded this edge is down here in the bottom. It might not actually recognize a bit of information until there, and then it's too late. Then nothing makes sense to it, so it just disregards it, or it tries to interpolate it. And yes, I make up my own words. It tries to interpret it to figure out what it's being asked to do. It depends on how the fixture or how the receiving device is manufactured as to what it does when it doesn't get good DMX, when it doesn't get a good signal. Some things try. Some things just ignore them, and they'll just sit in their current state. So it just kind of depends on what you have for a receiving device. But this is mic cable. This is why we definitely don't want to use it. The other thing that it has that it doesn't have is the twisted pair characteristics, which allow it to counter, interference. So this is the reflection that we saw. So you see it down here on the bottom. This was a lifted. So from the transmitter, we had plus, common, and then minus was lifted, meaning it wasn't making contact. So there was no negative signal being sent down. And this, what you see in the bottom, is the reflection coming back the other direction. So kind of interesting. I would have expected that to be negative and not lined up, but given how fast this stuff is moving, it's probably not lined up. It's probably just exactly what the engineers tell us is doing. We just can't replicate it on a scope because it's going too fast. All right, so the basics. Let's go back and talk about the things that we need to make sure we are thinking about. So 1,640 feet, it's kind of hard to get there nowadays, unless you're traveling over you have a set that's massive, because our multi-parameter fixtures are 40, 50, 60, 150 different parameters now. So you don't get that many devices on a line anymore. 32 devices is also becoming a little more difficult. again, because of how big each device is. But again, keep in mind that they're out there. The eighth load, quarter load devices are out there. Just check with the manufacturer. If you're looking to put 256 devices on a line, I would advise you against it, especially if you're going to use RDM, because RDM will probably fall on its face. And you will not get that two-way communication to even do something as simple as to configure them. So the daisy chain topology, so that's in to out, no T's and Y's unless you're using an optosplitter. Cable is very hard to come by that's not the proper impedance. So you see on the left-hand side in the picture, DMX512A is stamped right on the cable. So it's, you know that it's the right twist, it's the right capacitance, and it's the right gauge. And then your 120 ohm resistor terminator that you put on the end of the line, especially if you're using RDM. All right. Any questions? And then we're going to look at some pictures of. All right. You guys aren't asking questions, so this is going kind of fast. It's okay. So networking, we can definitely, if this gets done early, we can definitely come back and talk about more about networking because this is pretty light. So this is our new frontier. It is standard in many lighting systems, especially permanent installation systems. It might not be as readily available or as readily used in the rental market or on the sets, but it's out there in permanent installations. It gives us a lot more capabilities. So the piece of cable that we saw in the picture before, it gives us 512 things to talk to. A network cable can give us, multiple 512. So for an ETC system, we can do 64 universes. So 64 streets of 512. Also on that piece of cable, we can get remote processing. We can get remote viewing stations. We can get multiple consoles. It's amazing what you can put on a network. The great thing about it is the cable and the electrical components are all off the shelf. So you can go to any Best Buy if you have a switch that goes down and buy a switch and put your system back up online. You can't do that with an optosplitter. When you lose an optosplitter, you got to find another optosplitter. If you're in a small town that doesn't have a rental house that has one, you're going to be down. The biggest limitation on just basic networking is 100 meter segments. So that's 328 feet. You can increase that with fiber optics, but we're not going to go that deep. But I will show you some ways to get around that. So here is our simple daisy chain topology. So this is where I usually get class participation to try to, so if this Apex console or this console is the sending device and the fixtures on the bottom are the receiving devices, how does our wire physically hook up? Right? So we physically come out of the console and then we go from light in and out all the way down the line. So the length from that, from said transmitter to furthest receiver, I think that's the furthest receiver. I can't see the far right-hand side of my screen because the pictures are on it, is our 1,640 feet or 500 meters. That is basic daisy chain topology, simple, easy peasy kind of setup. That's really what we get to play with. So we get things that look more like this, where we have some fixtures on one side of the set or on the stage and then fixtures on the other part. How do we go about doing that? Well, if we daisy chain it, we literally have to run through the transmitter all the way through the receivers and then run a cable all the way to the other side of the set to pick up the other fixtures. Or we can use something called an optosplitter, and now we can come out of the console to the optosplitter and then go two directions. So there's one direction, there's another direction. Now, the question is, what are our links? Links. Well, we can go 1,640 feet from the transmitter to the optosplitter, and then we can go an additional 1,640 feet and 32 devices on each of these output lines. So we can now cover a pretty significant distance. So we got 1640, whoops, sorry. Was expecting another hit. What's missing over here is an additional 1,640 feet. Okay, this makes DMX very useful, very easy to set up, doesn't take much, and you're up and running. So let's look and see what this looks like with a network system. So there's that switch that I had mentioned. Some of you may have used one, may not really know how it works. We also refer to this as a star topology, if you think of a star, or a hub and spoke. So think back to your old wagon wheels from the Wild Wild West, where you have a hub in the middle and then you have spokes that go out to the different devices, and we can show that here. So there's a spoke to our transmitter. And then there's two more spokes to our, in this case, Dimerex. And then everything lives and communicates on the network. So I told you before that you were limited to 100 meters. So it's 100 meters to the transmitter, 100 meters to each of the maximum to each of the receivers. And then new term to keep in mind. So segment length is that 100 meters, and then your network diameter in this case is 200 meters. So that's the distance from the furthest point to the furthest point. So if each of your segments are 100 meters, your diameter is going to be 200 meters. So just like a circle. So that might not seem like it's very far. How would we get it farther? Well, we can add multiple switches. So we're going to use those same components. We have our transmitter. Now we have our two receivers, and then we have a section in the middle that connects the two switches together. So again, our segments are all under 100 meters, or in this case, exactly 100 meters, which means our diameter becomes 300 meters. So now we're still not to 1,640 feet, but we've definitely increased our reach. This is very common in a lot of permanent installations where there's going to be multiple equipment rooms throughout the building, multiple switches, and then these switches are going to be interconnected to get out and cover the distance. In some of these, especially some of these theaters that we have installations in, it could be several thousand feet between each room. And that's where fiber optic will come in, and they'll run fiber lines between the switches and then your copper wire from there. All right, so let's talk about a mixed topology. This is where it gets kind of fun, right? So our distance from our transmitter to our switch, we know, is 100 meters. And then we can have, in this case, is a gateway. So it's a device that can live on the network and convert network communication to DMX communication. And then we can have multiple runs of lighting fixtures connected to these gateways. So what do our distances look like now? So we have our networking system is still 100 meters. And then we have DMX that comes, so that's 200. Then we have DMX that comes off of that. That's our 500 meters. So now our reach is 5 plus 2, or 700 meters. So now we're covering an even longer distance than we could cover with just DMX all on its own. So this is very commonly what we see in permanent installations. I know that we as an ETC, and we're not alone, are have systems set up like this for even something as simple as a trade show, where we're sending network communication up to the truss, and then we have hardline DMX that runs out of these devices. This is the fun stuff here, because now we have lighting fixtures or receiving devices that live on the network natively, right? So we can now run network lines directly to these, in this case, lighting fixtures that not only have on board basically a switch, so we call it a node, but they're also have a gateway, which means this line of fixtures now resembles daisy chain, but electrically it's still a star. You're probably all looking at me like, what the heck's he talking about? That does not look like a star at all. Electrically, it's a star. So the components that are inside of the fixture do the electrical work to make it function and allow traffic to flow in two directions without colliding with each other. That's what the switches do. That's what the nodes do. As long as that stuff is in place, this system will function. So now we have the ability to hook our lighting fixtures up directly networked, which means we don't need to have multiple runs of cable, of DMX cable on our trusses anymore. Everything has the ability just to tell, for you to tell it what univert it sits on and then what its address is. This is the fun part. So this is the gateway part. So again, the same type of fixture can live on the network, and now it can also output DMX. So if I tell this bottom lighting fixture down here that it's on universe 1, and this particular fixture does 150 different things, but I can set this first fixture right next to it to be 201, and now DMX will come from that fixture to these other fixtures down below. So now our distances go all kinds of different ways. So we have our 100 meters, and then what you don't see up here is you got 100 meters between each of these fixtures. And then you got 100 meters to get to this fixture, and then 1,632, because it's hardline DMX at that point, going down the line. This is the fun stuff. Like I said, this is the future. This is what we're going to be doing. Whether a conventional lighting fixture gets an onboard node, I don't know when that will happen, because that will change the price of that fixture pretty dramatically. But as that technology comes down, we're going to start seeing it in more and more fixtures, which then means we can just run all our systems as networking. All right, so that is it for the slideshow. What other questions or what else do you guys want to know about to take up the rest of our 15 minutes?
I don't see any questions in here. Oh, Harry came up with one here.
Okay.
Why would you
I
use
have one.
two-way?
I have one. In this whole new system, is there a limitation to how many channels I can have?
Oh. Sorry, hit the wrong button. I want to do this button. Channels. Okay. This is a great time to have this discussion. So we have to work on our terminology now, because channel in one part of our industry means something completely different than it does in another part of our industry. So that's where I was kind of like hinting at the apartment complex and the mailbox concept. We also use the term feature. So a multi-parameter fixture has X number of features. So yeah, so the console is going to have a limitation on channels that it can that it can deal with. The infrastructure part is limited by whatever whatever the infrastructure is limited to. So I can't speak for all manufacturers. I can speak for ETC manufacturing because I use it the most, obviously. We can support up to 64 universes. So we can support up to 64 streets of 512. So do the math. That's like 32,000 something different addresses that a networked system could accommodate. However, not all consoles can speak to that many things. They're going to run out of channels. So if we can try to think of channels as what the console thinks of them as, and then on the other end is what the addresses are. Does that help any at all?
Yeah, you answered the question. 64 universes.
64, yeah, for an ETC system. I can't, like I said, don't take that to the bank for everyone else.
Why would you use two-way communication?
So the two-way communication is so DMX by itself is one way. So it's basically the transmitter tells the receiver what to do. RDM, remote something networking, remote device managing. I should know my acronyms better. It is a way that we can get information. We can send information to a device. So we can identify a device and tell it what its address should be. We could tell it what its operating mode should be. We can also ask that device information. So we can get information from it to find out what its address is, or what its operating mode is, or what its temperature is. Does it have an error? So that's the two-way communication now with RDM. Does that help, Harry? And that's where an unterminated line will really wreak havoc on that two-way communication.
Yeah, that makes sense. So can you talk a little bit more about like what differences you see? I think mostly our members are working in the commercial world, motion pictures and television.
Mm-hmm.
And I know that there have been a lot of devices invented in recent years that co-locate Ethernet switches and DMX and wireless DMX with power.
Mm-hmm.
Can you talk a little bit about how things are done in that side?
Yeah, that stuff's wireless. We have wireless native in our fixtures now. It's incredibly robust, especially since the FCC now really truncated the signal. So everybody kind of has their little swim lanes. And as long as people aren't outside of their swim lanes, it's very robust, especially for temporary quick setups. It's very robust. It's really no different. Wireless is no different than a cable. There's no physical cable. It's still, we're going to use the term universe. It still lives inside of a universe. The other part of your question was, refresh my memory.
Oh, co-locating with power.
Co-locating. Oh, signal. That's actually a very old technology where if you're talking about dimming down the high voltage line.
No,
or
it's
sending
just
communication down the high voltage line.
No, not sending it down the same line. Just that I think in my experience, what people do a lot on set is that they'll run a stinger to a light. You got a light that's going up for one setup, and then it's going to be down again in half an hour. And so you run a stinger to a light, you run a cable to a light. That's a control cable. So it's all home runs,
Yep.
right? Like very rarely would we do daisy chaining, and
Okay.
then in order to keep it organized so that you're not running cables to two different places, you have the Ethernet switch or the DMX node or whatever you have co-located with where the power is coming from, so that you're
Right. Yep.
plugging
Yep.
in the light, plugging
Okay.
in the
Yeah, I'm
a lot of
tracking.
yeah. So there's a lot of equipment that's been come along in the last, I don't know, 15 years, I guess maybe 10 years, that's intended to, what am I trying to say? Like integrate it all into one box.
Right. Yep. Sure. That makes a lot of sense. So that's going to be something along the lines of an optosplitter. So your transmitter, whatever you're using as a console, is going into optosplitter and gives you 8 to 10, 12, whatever the number is, DMX outputs. Yeah, and you plug power. So we tried, this is more of a power controls thing, but we tried as an industry to do dimming of like fluorescents and LED fixtures on the high voltage side, but dimmers, and it was horribly unreliable. So this remote concept now that we use, where we give the fixture power and then it has its own dimming on board, that it gets through the DMX line, is a far more robust and reliable system. So that's why now you're having to run 2 separate cables. Unless you do wireless, then all you give it is power, and then that data, that communications line is wireless. So that's why wireless is becoming very popular.
So I'm wondering about, I guess I'm wondering from the rental house perspective, uh, there's all this, there might be, what's the service of this equipment? Is anything serviceable?
In most lighting fixtures, there are serviceable parts. They're going to be like power supplies and some drivers and different things. Field serviceable, usually not. Then you're going to have, so your support equipment, so your infrastructure equipment, like your switches and things, those are disposable. So you run down to Best Buy or a computer store and you get another switch. Opto splitters are going to be very similar. There's very little serviceable inside other than power supplies. Yeah, that's kind of it. But yes, more and more these things are becoming more unserviceable, or at least not. It depends on how much you're spending on a lighting fixture as to how much you're going to get serviceable parts with it.
So let me follow up with a question about testing it then, because so how do people go about testing the cables, testing the opto splitters, testing the lights to make sure that this from
Yeah, that's a great question. There's a bunch of stuff out there for cable testers. Um, so it's like if you're doing network testing, if you just want to check a cable, that's one kind of tester. If you're wanting to check the electrical characteristics of a networking system, that's a different type of meter. But I would say most of you are probably just going to need a simple little pin check. So just checking the integrity of all 8 pins on a network cable and all 5 pins, well, really 3 pins on a network on a DMX cable. Yeah, there's really not a whole lot. I mean, there is in an installation, you're looking at some other like stuff in a networking system. You're also checking length. In a portable, in a studio rental house type, you already got to know what the length is because it's not in a conduit, it's not in the wall. You're just going to be checking the RJ45, which is the connector, has that little spring clip. You want to make sure that spring clip is still there. Otherwise, it just pulls right back out. Those are disposable. If you're going to get the armored cable, which Neutrix makes one, so then the armored It's the same Neutrix as the DMX connector. If you're using those, obviously those are not disposable. You want to try to keep those, but not all switchgear takes that connector, right? So it's kind of, they're great, they're awesome if all of the electronics in the middle use it as well. But yeah, that RJ45 has a very limited number of terminations. So those cables don't hold up very well in a portable type scenario, which is why networking really hasn't, in the portable world, hasn't really taken off.
Oh, you think that the cable and the connectors is a major reason that it's like a limitation? Because I know that when they do any kind of big rig, they always end up just starting from scratch, like with new connectors, new cable, and
That must be nice. I don't have that. I don't quite have that kind of budget.
well, if you were putting in a TV show or a big
yeah,
set that's
and
going to sit there for a
it's
couple
going to be
months.
there a while. Yeah. That's yeah. I can definitely see that is a very cost effective for no more than networking cable costs. Cat 5e, Cat 6 gets a little more expensive. We don't really, our networking, our communication across networking doesn't need Cat 6. Cat 5e is plenty for what we need. We don't communicate at a very high speed like computer networks do. It's getting harder to define Cat 5e. That's going to be the interesting part. Once there is no more Cat 5, Cat 5e, we'll have to go to Cat 6 and different connectors, and it'll be interesting.
Well, do anyone have any more questions for Patrick?
I got you to an hour.
This is, yeah, good job. This is your chance. Anything you want to know, we're afraid to ask.
Do you guys send out contact information? Like, if anybody doesn't want to ask a question here, they can just email me.
Sure, no, that's fine.
Absolutely.
Okay.
We do have another question in the chat here from Mario. Is there any tool to quickly test wireless DMX signal being sent from a transmitter to receiver? For example, I have a Lumen dim pix with no controller and want to test if the transmitter is sending to the receiver.
That's a great question, and that's something you should definitely email me, because I know that there is a so there's a thing called, I cannot say all the words together. So it's little s, ACN. So streaming is what the little s means, and ACN, Advanced Control Network. SACN viewer for copper wire will tell you everything that's on that copper that's being transmitted across the copper wire. That also exists for wireless as well. I'm going to say that it's going to be more than likely a city theatrical product, but I need to do some research on that for you. If you just want to throw or
I'm
can I
going to throw
throw?
your, or you,
Yeah.
you can. I was just about to do it. I have it ready to go, so I
Okay,
can
go
do it.
for it. Fire it away.
There you go.
Yeah, City Theatrical is one of the leaders in wireless communication in our industry right now. So I'm going to bet they have something.
All right.
All right, great.
Cool.
Patrick.
Thank you for the invite.
Absolutely. So, Allison, do you want to talk about the next EWI coffee break?
Yeah. Hold on one second. So just 1 week from today, we will be hearing again from our wonderful Patrick Stewart about the introduction to lighting controls with ETC, and this will obviously, and this will talk more about the types of consoles we're currently using, and how console technology is developed, and uh, what it kind of will look to into the future. And so that will build on sort of this information as well.